you to everyone who has joined us today. It's our second session of BitHacks Speaker Series 1. Today we have two special guests, Dr. Risto and Professor Justin Hart, who are both professors of computer science at UT Austin. And without further ado, Pranav, if you'd like to introduce the first speaker.
Yeah, okay. So the first talk is by Dr. Risto, a professor at the University of Texas at Austin and AVP of Evolutionary Intelligence at Cognizant Technology Solutions. His current research focuses on methods and applications of neuroevolution, as well as neural network models of natural language processing and vision. And he has authored over 400 articles in these research areas. Today, he'll be speaking about how we can use AI to make good decisions.
Yeah, ready to start?
Yeah, whenever you're ready.
Okay, I'll go ahead then. Yeah, so that's indeed the topic today, augmenting human decision-making using this evolutionary AI technology. So I'll talk first a little bit about what evolutionary AI is, and then I give a concrete example, which should be fun to follow. A lot of this work is actually joint work with my team at Cognizant, which is in San Francisco. I think we still have an office there, although I haven't been there for 6 months since the COVID. But also a couple of these guys like Santiago and Elliot are my students also at UT Austin. So this is the big picture. What we are doing is a little different from AI as it currently is construed in most of the around most of the world. So the current AI mostly is about modeling, that you come up with a large data set and then you use machine learning, some kind of stochastic gradient descent most of the time, to imitate that data set. So you already know that this is a picture of an elephant. You already know that this sentence has these words in it, or this spoken language has these words in it. So we are trying to get AI to imitate what we already know how to do. So that's modeling, that's prediction, and there's nothing wrong with it, but it's just part of what we could do with AI. Another part that we are focused on is using AI to create things that don't already exist. So this is a big difference. And here are a couple of examples of that. For instance, neural networks, deep neural networks, you can train them to do the imitation. But how are you going to come up with the architecture for that neural network? That's a creative question. And we can use AI to create these architectures automatically, make them better than what human can decide. I'm going to show this example in a bit. This is cycling through a number of web page designs. How do you come up with designs for websites so that the user who comes to the site is most likely to press that button that signs them up or buys something? Conversion optimization. Turns out there are people who are professionals on it, but we can still do better if we use AI and this creative AI to do it. And from the physical realm, this is Shinkansen in Japan, the bullet train. The first version had a very long, sleek nose cone, which is fine, except that it created a loud bang when it went into a tunnel. And in the version 2.0, the engineers wanted to get rid of that bang, but had a hard time doing it. And they used evolutionary AI to actually design a new shape. And this is what it looks like. It looks a little funny, but it does the job. And it's something that humans would have a hard time coming up with if it wasn't for creative AI. So that's the general setup. We want to take AI to the next level in the sense of not just imitating, not just predicting, but also creating things that don't already exist. Now, this is hard. If you usually solve a problem, you can do it with hill climbing, making small incremental improvements until you get something that's good enough. But if you are in a creative domain, there are many solutions. And how do you find the ones that are the best? The landscape where you're searching for those solutions might look like something like this. And there, if you are in some solution, you don't know what else exists and you don't know how to get there because you can't climb a hill. You have to go down before you go back up. So the space is deceptive in that sense. Also in creativity, it's very large. There are many different possible solutions and very high dimensional. There are many different design variables that you could change in order to come up with better ones. So that's where evolutionary computation comes in. And it's in contrast to techniques like stochastic gradient descent, backpropagation, and reinforcement learning. In those techniques, you have a single solution and you try to modify it step by step. Evolutionary computation, in contrast, is population-based. So you have a whole population of individuals, hundreds of them, and you initialize them so that they cover a large part of the space as broadly as possible. So this is like a cross-section of that previous picture, and you want your solutions spread out all around that space. And then you run search. And it's not just that you're doing 100 parallel searches, each one of those also talks to each other. So if one of those solutions finds something useful, like a partial solution, then you can recombine it with another solution that found something else. And that way you can find a peak that's a combination of all the good things from those two solutions. So there's some interesting demonstrations of how powerful this can be. If you, for instance, take a design problem of designing circuitry for a multiplexer, and you have 70 bits in the multiplexer, that's a search space of 2 to the 2 to the 70th. Looks like a very compact number, but if you actually print it out, not in this exponential notation, but in a decimal notation, it would take light 95 years to go from the beginning of that number to the end of that number. And that's the number of states where you're trying to find a solution. Yet with evolutionary optimization, you can, because you find partial solutions and then recombine them and gradually construct something that solves the whole problem. There are also demonstrations that you can optimize not just 5, 6, 7 variables at once, which is what humans can do, or are limited to 5, 6, or 7, or 10 or 15, like some of the methods in general Bayesian parameter optimization can do, but up to 1 billion variable task. So you can simultaneously turn 1 billion knobs in order to find a combination of those knobs that gives you best solution. This is Kali and Moydeb's work. And also there are techniques that when you're searching in this kind of landscape, you can get around these valleys by having multiple objectives and rewarding novelty, things that are simply new, not just based on their quality. Now, let's make this concrete. Let's look at an example and see how evolution actually works. And then we look at the COVID-19 example, the decision-making example. So here's a general setup for evolutionary computation. It is modeled after biological evolution, but it's all computational. So you have a population, and the population consists of genetic encoding, some kind of numerical encoding of individuals. So for instance, for a web page, it might list all the different things that can change and their values. That would be a one individual, and then another individual would have different values for those and another one different values. So you have a random sampling of possible web pages, each represented by numerical choices. That kind of a string is a good representation, string of numbers. It could also be a tree. But the point is that this is a genetic encoding that decodes into something that you can then test in the environment and see how well it works. And when you do that test, you associate the fitness to the encoding. And when you tested all of these individuals, then you can run evolution. You can do things like this, a crossover. You take part of a encoding of one parent and part of another parent. And then you take scissors, glue them back together, and you have an offspring encoding. And this is very much like in biology. Your genes, 50% of your genes come from your father and 50% from your mother. And that's how you get a new offspring genetic encoding. And evolutionary computation tries to capture on that. And this allows you to find those solutions in spaces that are so huge, because if you have a partial good solution here and a partial good solution here, you get a combination that includes both. And then you have some mutation also applied, which is random search and allows you to introduce genetic material when you need it. So this is how you generate new offspring. You throw away those individuals that were not measured to be good, and you replace them with the offspring, and then you iterate. So you always evaluate your individuals throw away the bad ones, keep the good ones, and recombine the good ones so that you get more and more offspring that performs better. So let's look at an illustration of that process. This is again the website design problem. So here are some of the things that you could change there and some of the values you could take. And if you list all of them, all possibilities, this is a very small problem, some 10,000 possible designs. Combinatorially, you just get them and you enumerate all possible combinations. But it's still a search problem. It's an interesting problem how you find the good designs. So here is an illustration of the search process through time. And now I like to think of my population as something I have on a desk. And they are the dots. Each solution is a dot, and this desk here is the search space. You try to find the best areas of the search space. And here, after I've evaluated the individuals, the dot here grows in size. So the best individuals are the largest dots, and the bad individuals are the small dots. So now I find 2 good dots, large dots, and those are the parents. So each dot represents 1 design, and now I pick 2 of the good ones to be parents, and then I form an offspring. Like here I take the background from A and the button color from B, and I get a new offspring. And I do that for many combinations of parents, throw away the small dots, and I get a new population. This is my second generation of solutions, and you can see that it starts to converge a little bit, and the dots start to get larger, and off I go. In a couple of generations, my population has focused on those areas where the really good solutions are. And in the end, if they're good enough, I stop and I pick some of the best solutions, and those are the ones I deploy. Those are the best designs that convert as well as possible in the world. So this is an evolutionary optimization, evolutionary computation process that allows you to come up with designs, new designs you don't already know that perform well. All right, so let's now take that into an example. And that example is in general decision-making, human decision-making. Can we improve upon that? Can we make better decisions by learning from past history and then discovering strategies that allow us to make better decisions? So in general, when you make decisions in anywhere in life, business or organizations or science or whatever they are, part of that decision-making is based on past experience, what you've seen work before, and then part of that is based on trial and error. You sometimes just try new things and see how well they work. So let's formalize that approach. Here's the formalization. We call the approach ESP for evolutionary surrogate-assisted prescription. And the reason is that there is a decision-making model, a neural network, and there's also a surrogate model, another neural network. So in real world, it's sometimes expensive to evaluate your decision-making in the real world. Like the web pages, we had to show them to 2,000 users in order to evaluate how good they were. And that's okay, but what if you're designing rockets or you're trying to make decisions on treatments on a disease? You cannot experiment on patients or rockets, that would be too expensive. So what you have to have instead is build a surrogate, something that stands for the real world, and we can just ask that surrogate, how good do you think our solution is? And that's enough to drive the evolutionary search process. You don't have to test your solutions in the real world. You test them with the surrogate, and you can test millions of them at the same time and for the same cost that you would test just a couple in the real world. So that's a crucial idea. And now the decision-making is in this triangle. We're looking at a context, which is a problem that's given to you where you have to make a decision, which is an action. And you use this model to map contexts to actions. And then each candidate is then evaluated by looking at its context action pairs and asking the predictor, how good are they? What are the outcomes? Will the patient be cured? Are there side effects? And that predictor is trained with historical data. So you have to have a database of context, actions, and outcomes. You use it to train the predictor, and then you use the predictor to train the prescriptor. So this applies everywhere. You can use it to design websites, recipes for agriculture, behavior for games, or allocating dollars in marketing. But let's look at something that's very timely, and that's deciding how to cope with COVID-19. And that means what kind of non-pharmaceutical interventions, NPIs, can we impose in order to keep the pandemic from exploding, while at the same time having minimal cost. So NPIs are things like close the schools, or close the workspaces, or keep the workplaces open but only at half capacity, close public transportation, or have require masks, things like that. Ban gatherings, ban large events. Those are the policies that you've seen already being imposed, but it's pretty haphazard right now. Nobody really knows how effective they are. So this is where we can bring in this evolutionary optimization. And based on historical data about what governments and municipalities and states have done in the past, learn what good decisions you could make. So this is new. Everybody is building these models on predicting what will happen in the future. How many COVID cases are we going to have in the future? And some of the people also take into account the restrictions, like how many cases are we going to have given that we close the schools. But nobody else, as far as I know, is trying to figure out what the optimal way of doing it would be. So not just what will happen, but how, what should we do about it? That's what we're after. So we build a predictor first with available data. And turns out there's data on cases and data on government restrictions that these guys have collected at Oxford. It's a huge job. They have to go to newspapers and find out what's done in different countries, but they have compiled such a data set. And now we can train a neural network model to read in the case numbers per each day, and then the NPIs that are active in each day. And this way we can build a time series and predict what will happen in the future. We also have an uncertainty model that tells us how reliable our predictions are. Once we have that, we can train another network. And this is now assigning the NPIs. It's looking at the same history of cases and restrictions, and then at its output is telling us what to do. You know, close workplaces, put restrictions on gatherings, impose stay-at-home requirements, whatever. Those 8 dimensions. Now, whereas we can train the predictor with historical data, here we have to evolve this neural network, use evolution, because nobody knows what optimal policies are. We have to discover it by trying them out against the predictor. And when we do that, we are evolving the predictors, and it turns out we have a population of prescriptors, those decision-making neural nets. And we start with a large population, and gradually as evolution progresses, we get a population that trades off those 2 objectives: minimize the cases and minimize the economic cost, minimize the closures, minimize the NPIs. So here, this is the number of cases. So some of these prescriptors are really good at reducing that, but they have a very high cost. So you, as a decision maker, can pick how many cases you can live with and how much economic damage you can tolerate, and pick one of these solutions from this Pareto front. So let's look at a demo of this. We have a interactive demo on the web, and if you go to this website, evolution.ml, you'll find it there and you can try it out yourself. So first you pick a country like United States by clicking on the map, and then you pick a prescriptor, whether you want to minimize cases, minimize NPIs, or something in between. What trade-off between health and cost do you want? And then you get the prediction of how the cases will develop in the future. And you also get the suggestion from the prescriptor what you should do. So if we pick something all the way to the left, minimize cases at all costs, then we get a prescriptor that closes down everything. Schools, workplaces, public events, everything. So it's much stricter than what we have today. But as you can tell, the cases will go down. That's the predictor. That's telling us that it will work that way. Now, on the other hand, if you don't like any restrictions and you open up everything, well, then you're going to have a lot of sick people, 150,000 per day. And this is what it would look like. Everything would be open, and you can go out and party, but there's a high cost to it. So you probably want something in between, and you can try some intermediate prescriptor, open things up, but not everything. And you see that this is actually pretty permissive, but the number of cases goes down a lot slower. And this is an interface that allows you to look at different countries like India. This is actually 20 worst countries right now, the highest number of deaths. India is still going up, so we actually have to be quite a bit more conservative there, impose more strict MPIs, go more towards the left in order to keep the pandemic from exploding. Here we are actually closing a lot of India in order to keep the cases going down. So, and this is interesting. You can see that different countries behave different ways. They are in the different phases of the pandemic, and you can try to see what you could do. So a couple of points. I think you're now back to the talk. I think you can see that. Workplaces and schools are really important. We find that consistently that we can open up a lot of other things, but workplaces and schools are always having the largest effect. And sure, those are places where people spend a lot of time indoors with a lot of other people. The transmission of the disease is quite likely there. So we have to be really careful about it. Another interesting thing that came out is this kind of alternation. So this is saying that keep the workplaces open, but then close them. You keep them open for a while, close them again. So this, remember that the evolution cannot really come up with just anything. It has to work with what's given to it as alternatives. And that's one creative way of opening gradually. And people are coming up with suggestions like that in the real world now. And it's interesting that evolution did discover it. We also find that we can go back in time. And for instance, in UK, turns out that it would have been possible to control the pandemic without closing everything down if they had acted early enough, and just closing schools would have actually avoided that explosion of cases they had. And also we find that different countries are different. Like Italy should have done better than they did with the MPIs they had. And the reason probably is that they were the first in Europe. We didn't know how hard it is. And also the culture in Italy is a little different than it is in China and South Korea and other places that were able to control the pandemic. So there are differences in culture and differences in population that could also be taken into account. All right, so the big picture here is we have an opportunity now with AI, with evolutionary AI and decision making, to build a future where the society is AI enabled. So the humans still make the big decisions about what kind of society we want. Do we want maximized performance? We want to conserve the environment. We want equality. Once we set those objectives, we can run evolutionary AI and come up with policies that achieve those trade-offs that we actually set. When I first put this slide together, I had really no examples, but now I have that one example on COVID-19 where it actually can be done. But you can see how it could be extended to other decision-making in society as well. And we are on the verge of doing that. Decision-making that's free of graft, free of personal agendas, and all this friction that happens in society. So to conclude, since I'm out of time, so ESP, this technique, utilizes a surrogate and evolution to do well in decision-making. And it demonstrates the power of data and machine learning in the real world, both in forecasting and being creative. And we can make it trustworthy. I didn't have time to talk about it, but we can create opportunities for people to understand the uncertainty and interact with it so they can convince themselves that they have the best solutions. And in that way, we can transform how we are making decisions. And if you're interested, here's a link. All you have to remember is actually evolution.ml, and you get to the interactive demo and some of the other demos. So that's what I wanted to say. Think I have 1 minute or two for questions if you have any.
Yeah, so if anyone has questions, please feel free to either unmute yourself or type it in the chat.
Right. Trying to find the chat window.
Yeah, so I can start with the question. So first of all, thank you for the very insightful talk. And so if I understood correctly, the premise is that good decisions are made based on past experiences. So it's necessary to adapt whatever worked related to a past experience to how well it would help in the current context. And you're suggesting a population-based search as the approach to try in the surrogate model.
Mm-hmm.
So do you expect the population-based search to be a time-bound or some sort of resource-bound exercise? Like
so first, the history is needed for the predictor. We need the population-based search to find something new, which is this decision-making strategy.
Yeah.
So the top part is predictor, this is prescriptor. So it's actually quite expensive. I mean, doing that search, population-based search, we are currently running this real time. Like every day there's new data that comes out. Well, as often as it does, we retrain the predictors and prescriptors, and we have to limit to 20 countries because that's the amount of compute we can do overnight. But that's the whole point. We couldn't do this before. Like deep learning came out, we had the ideas in the 90s for deep learning, but it didn't work because we did not have a compute. Fast forward 20 years, we have 1,000,000 times more compute now, and the ideas work. The same thing has happened in evolutionary AI. It requires even more compute because it's population-based instead of modifying an individual. And we are just on the verge of having that compute now so we can run it. Evolution is something that can take advantage of this massive computation that is available now. And indeed, that's why we can solve problems now that we couldn't just a couple of years ago.
Okay, yeah, and the surrogate model is basically like a simulation environment, right?
You could think of it that way. So we could use actual simulation, but simulation requires that you understand the domain, like first principles. You could do it in a physics domain, simulate the physics, but you can't really simulate how people behave under COVID. So it's a phenomenological model. It just looks at the outcome. It doesn't understand what actually happens underneath, but it serves the same purpose as a simulation.
Okay, thank you. Does anyone else have any questions?
Okay.
Sounds good.
Yeah.
Okay, thank you.
So thank you again for speaking. It was a very interesting talk.
Yeah, thank you. And go and take a look at the website. I hope you find this also informative and fun.